today's colloquium, we have the pleasure of welcoming Andy Sanders from the University of Illinois at Chicago, who's going to talk about Hodge theory and Riemannian metrics and character varieties.
Okay, well, thank you for the invitation. I'm happy to be here visiting old friends and hopefully making some new ones. I'm going to be here throughout the week, so if I say anything in this talk that either irritates or excites you, then feel free to come talk to me. I'll probably be in Brice's office or John's some of the time. So what I'd like to do for you today is kind of discuss a way of generating Riemannian metrics on spaces of representations of a closed surface group into a semi-simple Lie group. So our favorite example of such a thing is maybe the space of discrete faithful representations of a surface group into the isometry groups of the hyperbolic plane, which is the same as the space of hyperbolic metrics on the surface. And by the uniformization theorem, this space is the same thing as a space of isotopy classes of complex structures on the surface. And using this complex geometry a long time ago, I think it was first André Weil who realized that what's so-called Petersson pairing, which kind of came from number theory, could be used to define a Riemannian metric on Teichmüller space, which is now called the Weil-Petersson metric. And what I want to tell you today in a kind of meandering way, and mention a theorem at some point, is how this kind of fits into a much bigger story of using Hodge theory to build L2 style Riemannian metrics on spaces of representations of closed surface groups. So with that being said, let's get into some background. Maybe I'll just give a rough outline at the beginning here. And please, this is a colloquium, so please yell at me if I get too technical at some point or I'm saying things that are out of place. I will appreciate it. So the rough outline is we'll just kind of state the goal in writing, which I just quickly said in words. Then we'll kind of discuss some interesting representations which have been under intense study in recent years for G, say, for example, SLNR, just to give some motivation about why people care about studying these representation varieties. Then I'll kind of state the theorem I vaguely alluded to here and discuss some consequences or conjectural consequences. And then, although this is a colloquium, I still can't help myself. In the time that remains, I want to give a kind of very high in the sky overview of the proof. And really, I want to discuss the proof because I want to kind of draw the parallel that this is all motivated by studying how, if I fix a closed manifold and I pick a Riemannian metric, then using Hodge theory, I can understand the cohomology using harmonic differential forms. If I change this Riemannian metric, then I get some other space of harmonic differential forms. And this is somehow kind of the baby case of what understanding these types of Riemannian metrics, which shows that the things I'm going to build are going to be very hard to understand, but they also come from kind of a very special loved place in mathematics, so hopefully, though they're hard to understand, they'll be worth studying. Okay, so let's get started. So I'm sure no one has ever started with saying, let sigma be a closed, oriented, connected C infinity surface, and G, a semi-simple Lie group, okay, so e.g. SLNR, or SLNC if we want to talk about complex groups, or the symplectic group, or mixed orthogonal groups, these kind of things. Most of the groups that are coming to your mind are semi-simple Lie groups, unless you like the Heisenberg group, or Rn. Okay, so a representation rho of the fundamental group into G is reductive if, when I look at the composition of the adjoint representation of G, which then gives me a linear representation of pi 1 sigma into GL of the Lie algebra, if this representation is semi-simple. So in the sense of first year algebra and representation theory, this means if there's an invariant subspace, there's an invariant complement. Okay? So the character variety, slightly abusing terminology perhaps, the character variety is the following object. So I'll write it chi sigma G. And this is defined to be the space of all reductive homomorphisms of the fundamental group of sigma into G modulo G, where here the G action is by overall conjugation. By conjugation. Okay. So a type of representation that is not in this set is a representation that takes values in, say, strictly upper triangular matrices. Okay. If you like the terminology of Lie groups, the representations should not live in any proper parabolic subgroup. So most of the representations that arise as kind of geometrically meaningful things in this theory end up belonging to this set. But let me not say anything more about that. So it's a beautiful and deep story due to Atiyah-Bott, and then understood more algebraically by Goldman. This space chi sigma G has a, I kind of dislike using the word natural, but I think it's relevant here, a natural symplectic structure, which I won't define for you now, but I will say that if the group is complex, then this character variety is actually a complex manifold, at least away from points where it's not a manifold. And in that setting, this natural symplectic structure is a complex symplectic structure. So there's a holomorphic symplectic form. And this symplectic structure depends on nothing more than what you see here. So that's what I mean by natural. There's no auxiliary parameters one needs to put in. It comes entirely from the topology of sigma. In fact, just the combinatorics of the fundamental group and the fact that G is semi-simple so that its Lie algebra admits a non-degenerate bilinear form via the Qiongling form. Those are the kind of only two ingredients that go into the construction of what this symplectic structure is. So my goal today is to construct, and in the future I'll add study here, geometrically interesting, where geometrically will be left vague there, interesting metrics on, and I'll put in parentheses here, say subsets of the character variety, which are compatible in some sense, compatible with the symplectic structure. Symplectic structure. Okay, so what's the model of what my goal is here? Okay. So the model. So if we let capital script T of sigma, this is the Teichmüller space consisting of isotopy classes of complex structures on sigma, say, which agree with the orientation, then it's a basic fact, not so easy to prove, but a basic fact that Teichmüller space has a natural complex structure. And with that complex structure, Teichmüller space is biholomorphic to a bounded domain in C3G minus 3. It has a topology of a cell, but this is a slightly stronger statement. Okay? Furthermore, at a complex structure, and I'll blur the line between equivalence classes and complex structures, the basic deformation theory of complex manifolds developed by Kodaira and Spencer implies that I can model the cotangent space of Teichmüller space at sigma by the space of holomorphic quadratic differentials on this Riemann surface structure. So I'll write this way. So this is holomorphic quadratic differentials. So these are things that in a local coordinate for this Riemann surface structure, in a local coordinate z, if I have some alpha in here, alpha looks like alpha of z times dz squared, where alpha is holomorphic. Okay? And using this in conjunction with the uniformization theorem, which says to every Riemann surface structure, I can associate a unique hyperbolic metric, which has the property that the conformal class of that Riemannian metric belongs to the one defined by sigma. So given H, the unique hyperbolic metric, such that I'll write brackets for conformal class, is equal to sigma, and a pair of holomorphic quadratic differentials at sigma, then I can form the following pairing, which is called the Weil-Petersson pairing. I'll maybe write this way, which is up to a constant, which I'll suppress the real part of the integral of sigma of alpha beta bar over h. So what does this expression mean? Alpha locally looks like something that's a dz squared, and its complex conjugate locally looks like something that's a dz bar squared. H in conformal coordinates looks like something that's a dz times a dz bar. So this quotient here transforms like something times dz dz bar, which is a density which can be integrated over the surface. Okay, so this makes sense. I take its real part because obviously this will have an imaginary part in general. And the basic fact is that it took a long time for this to get fleshed out, but that this metric right here, Riemannian metric on Teichmüller space, okay, it's on the cotangent bundle, but be happy with a metric on the cotangent bundle instead of the tangent bundle, that this metric satisfies our goal. So WP is a Kahler metric, which means that the complex structure on Teichmüller space sitting here is parallel with respect to the Levi-Civita connection of this metric, if you like. And the associated symplectic form is, I'll just say ABG for Atiyah-Bott-Goldman. Okay? So what I'm interested in is the question of if instead of, oh, I guess I should also say something. So what is the uniformization theorem also saying here? I'm sorry, I got ahead of myself. So uniformization is saying there exists, in fact, a real analytic diffeomorphism from Teichmüller space to what I'll call f of sigma, which will be isotopy classes of hyperbolic metrics. Hyperbolic metrics, okay? And then a hyperbolic metric on a surface, when I lift it to the universal cover, I get a complete, simply connected Riemannian manifold of constant curvature -1, which is then isometric to the hyperbolic plane. And the action of the deck group gets conjugated into an action on the hyperbolic plane by isometries. So this is some subset of the homomorphisms of the fundamental group into the isometries of the hyperbolic plane, which I'll use the model PSL2R, and quotient by PSL2R eats up the isotopy class. This is Atiyah-Bott-Goldman. Atiyah-Bott and Goldman. Okay, so returning back to where I was, my original goal, which unfortunately, oh no, it's still there. My original goal says construct, study geometrically interesting metrics on subsets of the character variety which are compatible with the symplectic structure. So it turns out that by a theorem of Goldman, in fact, I think one of the first theorems of Goldman, the space of hyperbolic metrics identifies with one connected component of the space of representations here, consisting entirely of discrete and faithful representations. So that's all of them in this whole thing. And what we found is a Riemannian metric on here and a complex structure on here that's gotten by pulling back the complex structure on Teichmüller space through the uniformization map, which together give this thing a Kahler structure whose symplectic form is this natural symplectic form of the character variety. Okay? So this motivates us to ask if there's some generalization of Teichmüller theory, is there some generalization of the Weil-Petersson metric? And that's what I want to talk about today, although you'll see the answer is both very incomplete and very overdetermined. So are there any questions before we move on from here? Okay. So let's see if I'm going totally crazy here. All right. All right, so quickly, I want to say a couple words for motivation about what has been going by the name higher Teichmüller theory, which is really a shame because a bad guy like Teichmüller shouldn't get credit for things he didn't do, and there's really no complex analytic theory yet floating around for higher Teichmüller theory, so some people like to throw Thurston's name in there too. Maybe we'll lobby to have Teichmüller erased from history in this regard, but nonetheless, there are grants with this name in it, so maybe they're forever etched into history for this reason. Okay, so let's do the following setting. So there exists a unique up to conjugation irreducible representation, which I'll call maybe iota, from PSL2R into PSL-NR. One can realize this explicitly algebraically as the action by substitution on homogeneous polynomials of degree 2 and n-1 variables. Okay? And this allows us, by post-composition with iota, to put the character variety for PSL2R into the character variety for PSL-NR. So then a definition, the Hitchin component is the component of this character variety for PSL-NR containing the image of, and I'll say it this way, I'll say a Fuchsian component. So for experts, or maybe not even experts in the audience, in fact, there are two components in here of Fuchsian representations which correspond to the fact that sigma can have two different orientations. So when I want to say the component, I'll say the image of a single component. Of course, whether or not there are two Hitchin components depends on the parity of n, but let me not get into that at all. Okay? So this is this is all of the representations inside of here which can be continuously deformed to a representation in here followed by this unique irreducible representation. Okay? And so Hitchin discovered these things in 1990 using this complex analytic machinery called Higgs bundles. And they just kind of sat there with the exception of PSL3R, which had earlier been studied by Bill Goldman using geometric structures techniques. Otherwise, it all kind of sat there until the middle of the most recent beginning of this century, so about 2005, 2006, when Francois Laborie proved, by introduction of what are now called the Nazoff representations, that all Hitchin representations, reps, are discrete, faithful, and for all gamma in pi1 sigma, rho of gamma is diagonalizable, or I should say over R, with distinct eigenvalues. So these certainly share a lot of the properties that Fuchsian representations have. And somehow you should think of these things as, since the Fuchsian representations here correspond to hyperbolic metrics, you should think of these as somehow deformations of hyperbolic geometry on surfaces. And so with this in mind, I'll pose the following question to just have a more concrete question. Does, I guess, did I give it a symbol? Hitchin component, let's call it hit of G. Does the Hitchin component, named so because Hitchin discovered them, component admit a Kahler metric which, one, restricts to the Weil-Petersson metric on the set of Fuchsian representations, which include via this here, and two, which refines this Atiyah-Bott-Goldman symplectic structure.
So all Hitchin reps refer to the n? What is all?
So for any n and any Hitchin representation, yes. Yeah, thank you. Okay. So notice that this question has two pieces, because the only thing that comes down from the heavens on the Hitchin component is the Atiyah-Bott-Goldman symplectic structure. So I'm asking the question of, well, one, is there a reasonable complex structure on the Hitchin component, which is still an open question, if there's one that kind of you know is the right one. And two, is there a reasonable Riemannian metric that's compatible with that complex structure? And what I'm going to tell you about now is that although I don't know if there's a nice complex structure, there is an enormous parameter space of Riemannian metrics that do what we want. Okay, so I'll say Q, so an answer is unknown for n at least 3. What's the answer for n equals 2? Come on, you guys are worse than graduate students. Yes, right? So the Weil-Petersson metric does what we want for n equals 2, and we're looking to generalize that. So the answer is unknown for n at least 3. But what I'm about to tell you, implies there exists an infinite dimensional family of GI, where this is a Riemannian metric, and this is an almost complex structure. So an endomorphism of the tangent bundle that squares to -1, which may or may not be integrable, such that 1 and 2 are satisfied. 1 and 2 are satisfied. So while, and I mean, this is how it goes in a lot of these things. I mean, in a sense, this is nice, and the construction is nice, which I'm about to start to tell you about. But in these problems, the kind of integrability of an almost complex structure is the last problem you want to have. So this is the worst. If you have a list of things that you need to prove, and one of them is that a complex structure is integrable, you try to prove all the other ones first. So in a sense, this is kind of unsatisfying, but this is where we are at this state in time. But what I want to advertise with this is the potential power of infinite dimensional here. And when we see what this depends on, it encourages us that we might be able to use some kind of deformation theoretic techniques in this infinite dimensional space to try to go from an arbitrary one of these and go to a better one and a better one and a better one, and maybe find integrable complex structures this way. I mean, this is a very hard ball game too, but I'm here to advertise. So.
Can you repeat what condition 2 means?
Yeah, so remember, there's this Atiyah-Bott-Goldman symplectic structure everywhere that I haven't said anything about yet, but it's some symplectic structure. And I want that my Kahler metric, which has a symplectic form, is that symplectic form. Okay? Okay, good. All right. Ooh, good. Okay. So now, why don't I go ahead and state what the theorem says for you? Before I do that, maybe I'll ask, are there any other questions at this point?
Are you expecting this to be sort of unique in some sense?
So I'm gonna, after I tell you what the theorem means, I'll give you some ideas about how one might pick out a unique one. Me and Brice go back and forth in this conversation, and I think he's a stronger believer than I am that there's a hope that there's some kind of singular best object. But there is a conjecture due to Francois Laborie, which suitably interpreted kind of says that there's one that you kind of do a similar procedure which you do to find Weil-Petersson, and if the conjecture is true, then it'd be sensible to call that one the unique one, and I'll get to that shortly. Okay, so let me state the theorem now, and I'm going to try to put it over here and then leave it here so that later when I talk about its proof, I have something to refer to. Okay, so here's the setup. So theorem, and I should say, well, this is often true in mathematics, but I mean, this theorem is inspired by a number of similar constructions, which I'll give references to at the end, but let's state the theorem first. So let's just take U, some open subset of this character variety, open subset. Okay, and now there's an issue with, I mean, this object here is usually singular, but it has lots of parts that are not singular. For instance, I should mention this here, that the Hitchin component for SL and R, PSL and R, this is diffeomorphic, which was also proved by Hitchin, to a cell R to the, oh God, minus Euler characteristic of sigma times, I guess, n squared minus 1 is the dimension of PSL and R. Okay, so if I'm talking, I mean, if I replace this with the Hitching component, then open subset means it's a manifold. I kind of want to stay away from the singularities here, but this is kind of a technical issue I don't want to get into. So if you like, when I say open subset, I'm assuming some open subset that belongs to some part of this guy. That's a smooth manifold. Okay, and most of this guy is a smooth manifold in some measure theoretic sense. Okay, so let's take an open subset and take P, which is just any smooth map, any C infinity map to Teichmüller space. Okay, then there exists. So you might guess now that, oh, it got erased. Oh, no, it didn't. That infinite dimensional here comes from this condition right here. Okay, so this is the parameter in this construction. Okay, so then there exists one G, and I'll write sub P to denote the dependence on this map, a Riemannian metric on U. 2, I sub P, an almost complex structure on U. I guess I have to go over here now. Such that, I should say almost complex structure, which is GP orthogonal. So 3 is that if I look at omega I sub P, so when I have an orthogonal almost complex structure, there's an associated 2 form that you get by the following prescription. So this is its definition here. The associated pre-Kahler form, if you like, is the Atiyah-Bott-Goldman symplectic form. Okay. 4, if G is complex, so this means that this character variety now is a complex affine algebraic variety. So on its set of smooth points, it has a complex structure. So I'll denote that the associated almost complex structure is its almost complex structure by J. It's almost complex structure. Then something else I like very much happens, which is that.
You're saying it's almost because why not?
Oh, well, no, I mean, this almost complex structure is integrable, but on a complex manifold, every tangent space is a complex vector space, and this is multiplication by I in the tangent spaces. The other way around, if I just have an endomorphism that squares to -1, that might not be a complex structure in the tangent spaces that comes from an honest holomorphic atlas on the underlying manifold.
This J, I think you mean is the almost complex structure of the character.
Oh, yeah, yeah. Thank you very much. Is what I get for being too brief, is the associated almost complex structure on the character variety here. Then, when I look at the composition of these two almost complex structures, they anti-commute, and hence define a third almost complex structure, which I'll call K sub P. So I have now 2 linear endomorphisms of the tangent space, which anti-commute, which defines a third linear endomorphism, which also squares to -1. So this generates an action of the imaginary quaternions, or even the full quaternions on the tangent space. So, so this could rightly be called a quaternionic structure, but more is true. And if I look at omega IP, which is this object here, which we already know is equal to this guy, and I add to him I times omega kp, so this is the same object, but I put k sub p here, is the holomorphic Atiyah-Bott-Goldman symplectic structure. So this means that on face value for a complex group, this thing is a complex symplectic manifold. That's kind of its natural geometry that comes from topology and the structure of the group. But anytime I pick a smooth map like this, I can find a Riemannian metric in a new almost complex structure such that the pair, or the tuple, say GP IPJ, is what's called an almost hyper-Kahler structure. So a hyper-Kahler structure would be I have three complex, honest, integrable complex structures that generate an action of the quaternions and a Riemannian metric such that the pair of Riemannian metric in any of them is a Kahler manifold. So almost here refers to the fact that we don't know this complex structure here is integrable. Okay? So the motivation for working on this, which I've been working on things around this with Brice for a long time, is to understand kind of what controls all the different possible hyper-Kahler structures that can appear on this guy. And so, I mean, this is a kind of promising step 0 in that direction, showing that if one does not require the integrability, then there is a really huge number of these things. Okay, so let me just finish by saying, wait, let's see if I want any comments here. So yeah, so now let me say, so what happens for special P? So this is the end of the statement of the theorem here. So what happens for special P and special U? And U. So if I said this is a generalization, I would hope this theorem spits out things that I've seen before. And indeed, that's the case. So what's the simplest possible thing I could pick? I could pick U to be everything and P to be a constant map. Okay? So so if U is basically anything, but let's call it everything, and P is constant, so we'll say P of rho is just some fixed sigma in Teichmüller space for all rho in U. Then, well, in particular, IP is integrable. But it's not just integrable, it's something I knew before. In fact, so GP, IP, and in parentheses, J, if the group is complex, this is the hyper-Kahler structure of the space of so-called Higgs bundles. So I'm saying this for people in the audience that might have some familiarity. Don't make me say anything about what Higgs bundles are. But Higgs bundles are some kind of moduli space that when you pick a Riemann surface structure, you get a space which is homeomorphic to the character variety. So it's some new space that uses complex geometry that you build once you pick a Riemann surface structure. But it turns out that there's sufficiently enough structure in the world of complex geometry that these moduli spaces you build come with hyper-Kahler metrics. And they're kind of mysterious and strange to understand, but I like this interpretation of it because you recover these structures that require you know what a Higgs bundle is without knowing what a Higgs bundle is, which this word turns a lot of people off. So although I like Higgs bundles, I try to keep people happy. So this is one case. What about if U is what I was calling f of sigma? So this is the space of hyperbolic metrics, which is the same thing as the space of discrete faithful representations into SL2R. And P from Fuchsian space into Teichmüller space is just what I like to call de-uniformization. So this just takes a hyperbolic metric and only remembers what its conformal class is. Okay? then this pair is the Weil-Petersson Kahler structure, WP Kahler structure. Okay. And I should say that this process is functorial in a number of ways, so I'll just say these out loud. So a lot of people care about the action of the mapping class group or the action of the outer automorphism group or the fundamental group on this object here. So the mapping class group is the isotopy classes of orientation-preserving diffeomorphisms of sigma, which act on a representation by pre-composition with the induced map on fundamental group. Okay? And let's say I want my structures to be mapping class group invariant. Well, it's the simplest thing to ask is that P should be equivariant. Then P should be mapping class group equivariant. So it's functorial in this way that if I pick a map which is equivariant for the mapping class group action, then the mapping class group acts on this almost Kahler manifold by automorphisms of that almost Kahler structure. Okay? Furthermore, although there's not really that good a reason to state it this way, but I just want to emphasize that what's going on here is kind of a sheaf theoretic statement. I'm saying every time you give me an open set, I hand you some object. And so what this really is some kind of morphism of sheaves happening here. But I don't want to say any more than those words. But I think the kind of it's kind of obvious that the construction should be local, but once you state it this way, it gives you kind of new ways to think about how you might try to study them. Okay, so that's enough wandering around. So maybe before I get into talking a little bit about some of the consequences, I'll pause for questions again.
So you're saying that if you take a smaller u, then you get the restriction?
Yeah. That's right. Okay. All right, so what are we doing? Oh, good. So I have like 15 more minutes because we started 5 minutes after. Is that right? Okay. So let's say something about your question about what a uniqueness statement might look like. And then in the few minutes that remain, I'll bore you with a very loose sketch of how this works. Oh, no! If P U from Teichmüller space sigma, this is inside chi sigma g, is C infinity, then there exists. Okay. So this theorem turns a question about what a uniqueness statement might look like to the question of, is there a best way to pick a map to Teichmüller space? And in fact, there's been a conjecture around for quite a while now due to François Laborie that translated says exactly this, that there's a best map here. Now, one could argue about this because constant maps seem pretty good too. So, I mean, there is some play here. But the constants maps certainly fail to be mapping class group equivariant, which depending on your taste, maybe you very much don't like this. So conjecture of Laborie, the current state of this conjecture is that it is true for n is equal to 3, and for a couple groups other than the special linear group, which are rank 2 groups. But let me state the conjecture first in reference to this, and then unwind it a little bit, is that there is a really good mapping class group, which I'll say mod sigma, equivariant map P from the Hitchin component for SLNR into Teichmüller space. Okay, so what does really good mean? Well, one thing it means is that P restricted to Hitchin SL2R, this is just the same thing as Fuchsian representations, which are sitting inside of here, this is what I called over there de-uniformization. So when you restrict to a Fuchsian representation, you always just spit out the conformal class of the hyperbolic metric that representation uniformizes. Okay? But moreover, this map is kind of, in a Riemannian geometric sense, I'm about to say where the map comes from. In a Riemannian geometric sense, the kind of most natural thing you could do. So when I take a Fuchsian representation, I can ask the following question. So if I have a Fuchsian representation, discrete and faithful representation into PSL2R, I can look at the space of all equivariant maps from the universal cover here to the hyperbolic plane. Equivariant, so F, equivariant. Okay. Okay. And then I could ask for various special classes of maps. Okay. So I could ask for the following condition, could ask for a conformal structure in Teichmüller space such that there exists F from the universal cover of the Riemann surface defined by that conformal structure into the hyperbolic plane, which is conformal. Okay. Now this is again just basically the statement of the uniformization theorem. We know this is true, right? This thing uniformizes the hyperbolic metric, so over here I see the hyperbolic metric. Which conformal structure do I pick? I just pick the one that underlies that hyperbolic metric, and I know that there's a conformal map from the universal cover of my surface to H2 that's equivariant, because I know that the hyperbolic surface is the same as the conformal surface by the uniformization theorem. So a Riemannian geometry way to put this is I want to find F that is row equivariant and totally geodesic. So that turns out to be equivalent to this statement. Okay? So what is this conjecture? So conjecture actually, due to Laborie, is that for all rho from pi 1 sigma into SLNR Hitchin, well, let's think here for a second. Does it sound very reasonable to ask for a row equivariant totally geodesic map of the universal cover of sigma into what should replace here? Well, H2 is the symmetric space for SL2R, so I should look for the symmetric space here. And even in symmetric spaces, totally geodesic maps are not abundant enough to care for a huge parameter space of representations. So relaxing that, the next best thing, we ask if for all Hitchin representations, there exists a unique F row from the universal cover into the symmetric space for SLNR, which is a minimal surface. Minimal surface. Okay? Okay? So this means if I take locally a little disk around a point here, and I map it over to here, and I look at all the disks over there that have the same boundary curve, this one should have the least area around that boundary. Okay? So this is his conjecture. And then from this, what do I do? Well, it turns out that although minimal surfaces don't have to be immersed, even though in this case they actually turn out to be, the pullback metric, which is some tensor over here, always defines a Riemann surface structure here. So if this conjecture is true, so if this is true, let's call the metric over here maybe Q, then my map from the Hitchin component of SLN into Teichmüller space, I just take rho and I take the conformal class of this pullback by the unique minimal surface. Okay? And so I should say that this is true this theorem is true for n equals to 3. And one of the inspirations for this construction was a paper of Qiongling Li in which she constructed the metric that I'm talking about here in the case of SL3 using this map. So really, this theorem is just a kind of re-understanding of what was going on in her paper, although I mean, it's much more general, but it follows the same basic idea. And so in the last 7 or 8 minutes here, let me tell you what that basic idea is. Okay? So we're inside the final 10 minutes, so I don't have to make sense anymore, right? So actually, let me just to say I'm addressing your question here. You know, one might say if this conjecture ends up being true, and its proof is not easy. I mean, for example, by its proof, one sees no reason why it should be true in general, but no one has any idea why it's not true. So if it turns out to be true, it's kind of, after years of thinking about it, you're kind of compelled to think that the map you get from it is very good. And maybe since this process, as I hope you'll just see, is kind of quite natural, if there is a good map floating around, it sure looks like this is a damn good candidate. Okay, so let me, in the last short time here, just say a little bit about the proof. And so I haven't talked about Hodge theory at all directly here, so let's bring that in. Okay, so this has serious quotation marks around it. So I want to encourage you to consider the following situation. Let's just let M be an oriented closed manifold.
So what is this a proof of?
The construction of this theorem here. No, I'm not going to present a proof of this conjecture in 5 minutes. It wouldn't fit in the margin of the page. So let M be an oriented closed manifold, and consider the space of all Riemannian metrics on M, which I'll denote that way, and the trivial vector bundle over this, which is just metrics on M times the kth de Rham cohomology for your favorite K. Let's just pick one, for instance. Okay? Okay, so this bundle admits a bundle isomorphism to a bundle that is not so obviously trivial, which I'll call H upper 1 over met M. And this is the guy, maybe I'll call that map pi, such that the fiber over pi is equal to the harmonic one forms with respect to G. Okay. So this is an example of something that, although it's usually not talked about out of Kähler geometry, of what you might call a variation of Hodge structure. So the Hodge decomposition on the forms is what leads to the fact that for every de Rham cohomology class, you can find a unique harmonic representative. And I want to study how the harmonic representatives vary as I vary the metric. Okay? And now, here I had a cohomology group. So although one forms on a Riemannian manifold, there's an L2 product on those, an L2 inner product. It doesn't descend to cohomology because it doesn't respect changing cohomology classes. But now I found a vector space. So I took a bundle that came from a quotient of some space with an inner product that lost its inner product. But then I used Hodge theory to get a vector space again. And now there's an inner product here. So what I'm trying to advertise with this simple thing is that basically this is the proof of this theorem, modulo the fact that this nice, easy cohomology group maybe here gets replaced with some more complicated cohomology group. And a slightly more, although completely standard, application of Hodge theory needs to be used. So let me just say quickly here. So now the replacement for met M is this open set U. Okay? And over U, I don't have something simple like this, but I want to put a Riemannian metric here. So I'm going to put the tangent bundle of U. Okay? So So here's the fact, is that the tangent space, or maybe I should call it a class, at the class of this representation is given by the following thing. Well, I'll write two isomorphisms. It's given by the first group cohomology with coefficients in the Lie algebra of G, where the action of the fundamental group of sigma on the Lie algebra G comes from composing the representation with the adjoint representation. But by the souped up version of the de Rham theorem for local coefficients, this is also a cohomology group of differential forms that have values in something slightly more sophisticated than R, but something that R is an example of, namely a flat vector bundle. So this is isomorphic to the de Rham cohomology of sigma with coefficients in something I'll call E sub rho. So this is a vector bundle with a flat connection, nabla, with holonomy rho, with holonomy equal to rho. Okay? So again, what does this exactly mean, this group? So this is the kernel of some differential operator, d nabla, divided by the image of nabla, where this d nabla and nabla sit in the following chain complex. I have sections of this flat vector bundle. A connection takes a section to a one form with values in sections. And then the connection always extends to what's called an exterior covariant derivative, which bumps you up into the next highest form. So this is called d nabla E rho, and we're on a surface, so we're done here. And this group is exactly the kernel of this linear differential operator here, mod the image of this one. And it's kind of a basic fact that coming from the identification of representations with flat connections, that this is a model for the tangent space here. Okay? So now, since I don't have time, I won't go through the construction. But the point is now using the fact that associated to rho, I have some conformal structure because I have this map down to Teichmüller space. And the theory of harmonic maps, the fundamental theorem being due to Corlett, there exists a metric on E rho, which comes through some slightly complicated procedure, but its exact needed input is rho and sigma. Okay? And then using this, the space of one forms with values in E rho has an L2 pairing, which exactly looks like the L2 pairing on differential forms. You take two K-forms on a Riemannian manifold, you take alpha wedge star beta, and you integrate. And that's the L2 pairing. This looks exactly the same. Now I have one forms with values in some flat vector bundle, but I have a metric on the bundle. So a one form with values there looks like a one form tensor a section. I take two things like that, and I alpha wedge star beta the one forms, and I coefficient pair the sections with the metric here. And using all this, slightly more sophisticated statement of the Hodge decomposition says that this is isomorphic to a space of harmonic one forms on sigma with values in E rho. And now, just as in that example I mentioned, that L2 metric, which was not well defined on cohomology classes, becomes well defined on this vector space of harmonic forms. And since I'm over time now, I won't totally destroy your lives by talking about the almost complex structure and why the properties are satisfied. But essentially, the almost complex structure is an elaboration of the fact that star squared is equal to -1 on one forms. So on a Riemannian surface, the Hodge star operator is the almost complex structure. And this, in combination with a naturally constructed object, gives you an almost complex structure here. And then you just are happy and compute with some formulas, and all of these properties of the metric are satisfied. So the mysterious part of this construction, and the reason why it's impossible to know if these complex structures are integrable right now, is what one needs to understand is what these harmonic forms look like and how they vary as rho varies, and how that dependence depends on the smooth map I chose. And it's some kind of outrageous magic of the uniformization theorem that this completely intractable sounding problem ends up being fairly well understood. And I hope at some point I'll come back here and tell you that this is slightly better understood. So thank you.
Any questions for Andy?
Did you say that the mapping class group acts? How does the mapping class group act on phi? Maybe
On
phi of sigma g?
yeah. So if I have a diffeomorphism of the surface, then I get an induced map on fundamental group, which in fact doesn't care what the homotopy or isotopy class of this guy is. So then I have rho, and I just go to rho composed F star.
So, I mean, in the case where G is a complex group,
Yes.
phi of sigma G is, I suppose, an affine variety.
That's correct. That's correct.
And the mapping class group quotient is what?
Well, it depends. So one thing I can say that, so let's take SL2C, where this is already an extremely interesting question. So the space of discrete faithful representations of a surface group into SL2C is some closed subset. It has an interior, which is known as quasi-Fuchsian space. So these are quasi-conformal deformations of Fuchsian representations. And it's known for a long time the mapping class group acts properly there. And it is a conjecture that it doesn't act properly on any larger open set. Now, it's known that, so you have this subset inside the SL2C character variety. Here, the action is proper. On the boundary here, it's super crazy. What's unknown is if there's some dude out here where it's also proper. But it's a conjecture that the maximal open set upon which the action mapping class group is proper is here, and it's a conjecture on the complement that the action is ergodic.
So is it believed that the quotient on the nice part is again an algebraic variety?
Well, it's, let's see what I'd like to say about that.
I mean, because then you could sort of ask that P be a map, the T descend to the quotient.
Yeah, I mean, this is certainly the kind of,
Be an algebraic map.
yeah, I mean, this is kind of a big goal of this whole theory, to kind of move from representation spaces to moduli space. But, I mean, I think I have to say I don't know the answer to your question. And maybe the question about whether or not the quotient isn't, well, so let me say this. Where this action is proper, it turns out that biholomorphically, this set is Teichmüller space cross Teichmüller space, and the quotient is then moduli space cross moduli space. Moduli space is a quasi-projective variety. So there is that to say, but.
So I mean, if the quotient were an algebraic variety and you required P to be an algebraic map, then it would be probably unique, because a map, it's very rare that it exists an algebraic map between two algebraic varieties. There is zero of them. But
that's a very interesting. That's a very interesting comment, actually. Thank you for saying that. Yeah, that's great.
Well, yeah, the equivariance, if you required then P would be a map.
Then it goes to a map to moduli space and a map to some object here.
Projective variety of some dimension. This would be a projective variety.
Yeah.
If it's an equivariant map.
Sorry, I'm just thinking the conjectural Laborie map would not be algebraic.
It would not be. No.
Be real individual.
Yeah. But that's still a very interesting comment. I mean, I'm not completely.
No, right?
It's not inconceivable.
Well, is it not just kind of this conjecture to be this forgetful map of this bundle of differentials back to Teichmüller space?
Oh no, that complex structure is probably. I'm not sure that one's the right one. So.
The right
I don't know, can you prove for SL3R, for instance, that, I think, the thing is that,
Yes, it's not the same.
you can't tell it's the same, and from its face on the bundle over Teichmüller side, you can't tell if it's compatible with anything as far as I can see. So it could be, yeah, the map could be holomorphic. It's not inconceivable.
There is a complex structure in which it's conjectured to be holomorphic, but it's probably not this one. But people don't know. Does that sum it up?
I think that's a reasonable statement, I believe. Yeah. That's a very interesting comment, though.
Okay, other questions? All right, so let's thank Amy again.